So the stream of air is coming in this direction, which is characterized by the M node. So this M node dot is representing the area of inlet with rho V. So area rho V gives us the mass flow rate in the kilogram per second of the air is entering to the system. From the sidewise, you have MS. Okay, so just simply taking the XYZ Cartesian coordinate at this point, mass of fuel is entering into the system from the fuel tank. And this fuel and oxidizer mix together within the combustion chamber, so it will take place, combustion will take place. And the mass of air plus the mass of fuel is coming out. Okay. The mass of air, the mass flow rate of air plus the mass flow rate of fuel together comes out. That is the hot gas. Okay. So this hot gas is coming out here. Okay. So this is just a general system for momentum balance, and the momentum out minus momentum in the x direction, just the flow direction is considering in the x, considering the quasi one-dimensional flow, and assuming the steady uniform flow, we have the simplest form of momentum equation. So the net fluid that comes out from the system is equals to the summation of momentum in the x direction out minus momentum in, which gives us the net force in the x direction of the fluid net force. So that equation states that the difference between fluid, which is the time rate of change of momentum out of the boundary and into the boundary, is equal to the net force acting on the fluid in the x direction on the boundaries and within the given box. Okay, so this is the equation, right? So the contribution of each component to the momentum balance of the above equations, we have x component here. So mx out is the summation of force in the x direction. Momentum in the x direction out, which is equal to m naught plus mf at g9, because here this is the 9 condition. So m naught plus mf is here. Okay, so v9 means exit velocity here. So this times exit velocity plus rho naught v naught times a minus a9. So this is the net difference between exit area and the inlet area and exit area. Okay, so v naught is the velocity from that point. So that is in the x direction. Again, this is out actually. And in the in direction, rho naught v naught a times v naught plus ms v naught. So that is this condition. M naught is there, rho naught v naught is there. Again, ms is there, ms times v naught. That is one mass flow rate. Okay, so summing them, we can have in the inlet condition, the outlet condition, and the net flow is minus of F fluid minus. So this minus of F fluid is what we call the momentum thrust component, and minus G9 minus G naught times area 9. So this is the pressure thrust component, which we have discussed before. Okay, so this component is the pressure thrust component, and this component is the momentum thrust component. So we will sum up these things together. So this is the inlet, outlet, out and in condition, and this is the net. Okay, so these equations provide us an appropriate derivation for. So when we apply all these three equations applied to this condition, this is equals to no, the F net is equals to F out minus F in. That gives us this equation. And after some simplification, finally, what we can get is M naught dot plus MF dot times VG or V9 minus M naught V naught, which is equals to minus of Fx of the fluid minus G9 minus, no, P9 minus P naught at the exit condition, actually. Okay, so this is the simplified form of momentum equation. And then considering the action and reaction condition from the Newton's second law. Actually, not Newton's second law, but Newton's third law, the action and reaction, which are equal in magnitude but opposite in direction. So just considering the x or axial forces only, we have finally this kind of equation. The question 13 is the net force. So thrust force is equals to exhaust momentum through the nozzle plus minus the inlet momentum, which contributes to negative to the exhaust thrust in the effect. It represents a drag force. Actually, this is the drag part of the force. And the pressure area term. So this is the pressure area term, this is the momentum term, and this is the drag component. Okay, so in our previous initial equation, we didn't consider the drag component. Okay, so this minus sign indicates it contributes to the drag. So this mass of oxidizer or oxygen plus mass of fuel together, we call it as mass M. M simply. That means the total mass of the mixture. Okay, fuel oxidizer mixture, which come out from the combustion chamber. So this can be represented simply M. That's why we have this component and this component. So this force, the force given here is called uninstalled, net uninstalled thrust. It is called net uninstalled thrust, and it is represented by Fn uninstalled. So this is a representation. You can rewrite it with Fn uninstalled is equal to M naught plus Mf times V9 minus M naught V naught plus P9 minus P naught the whole times A9. So this is general thrust equation considering the drag term also. Here, three different terms are there. One is this is the momentum term. It is positive. This is drag term. It is negative. This is pressure term. So this pressure term, it can be either negative or positive depending on the value of P9 and P0. P0 is already known, but what is the value of P9? That means exit pressure. Okay, so based on that, we call it as overexpanded, underexpanded, or optimally expanded nozzle. So it is a nozzle condition actually. So momentum thrust, pressure thrust, and drag component of thrust. Okay, so the inlet momentum, which contributes negatively to the engine thrust, in effect, it represents a drag term, or simply the penalty of bringing air in the engine with finite momentum. So this negative term is because of the finite momentum condition. So it is called ram drag. Another name of the drag term is called ram drag. So d ram is equal to m naught v naught. So once it is drag, we are not representing it with minus sign here. So the last term is pressure area term, which is called pressure thrust, which act over the nozzle exit plane area, A9, and will contribute to the engine thrust only if there is an unbalance of static pressure and the ambient pressure. Static pressure is the exit area pressure. The exit pressure is static pressure. Again, this ambient pressure is also static actually. It is the pressure of the atmosphere, which we know. But P9 is the exhaust jet, the jet pressure. So both of them are static in nature. So if P9 is greater than P0, the condition is there. If P9 and the P0 are equal, then pressure thrust condition becomes. Hello.
ተቋርጦ ነበረ።
እየሰማችሁኝ ነው?
አሁን ይሰማል። ተቋርጦ ነበር።
ረጅም ሰዓት ነው።
አንድ 3 ደቂቃ
እንዴ ረጅም ሰዓት ነው። ፉሊ ስለዚህ ምን አካባቢ ነው እንትን ያለው? እስቲ ንገሩኝ። ስላይዶቹን
ራም ድራግ የሚል
ይህን አይተናል። ኦኬ ሶ ይሄን ካየን how about this
አይተናል።
ኦኬ ሶ የዛ ተመሳሳይ ነው። ኦኬ ራም ድራግ አይታችኋል?
እዚህ ላይ ነው የተቋረጠ።
Okay, so this is the ram drag, which is the drag contribution. And the last term here is the pressure thrust. So it is just for thrust due to pressure is P9 minus P0 times area 9. So which is called pressure area term and which is act over the nozzle exit plane. So based on that, pressure thrust component, we have 3 distinct class of expansion in the nozzle. So from aerodynamics view of point, a nozzle with subsonic jet will always expand the gas to some static pressure as the ambient condition, where as in the sonic or supersonic exhaust, jet may or may not have same static pressure in the exit. If it is having positive static pressure at the exit, so it contributes for the thrust again. So depending on the mismatch of the static pressure,